We're sticking with weak interactions for one more video here because we're going to do Feynman diagrams. Now, if you're OCR, you don't need to watch this because it's not on your spec. AQA, it's definitely on yours. And EdXL, I'm sorry, I can't remember. You'll have to check your specification for Feynman diagrams. Right, so these are the three weak interactions that we just seen that we need to know about. And the Feynman diagram is a way to draw weak interactions, and it's a really helpful way to represent it first of all, but also it shows the exchange particles that we talked about earlier. So here is beta decay first of all. In a Feynman diagram, the particles that you have before are always shown at the bottom, and then time sort of moves upwards. Imagine a time axis there. So in beta decay, you have a down quark, and then there's going to be a weak interaction, and it's going to turn into all those things. So here's the down quark first of all, and the first thing that happens is it throws out a W- boson, and that turns it into an up quark. Now notice the conservation laws are all met in that moment, that interaction, because we've got a third of a baryon turning into a third of a baryon. We've got a lepton number of 0 and afterwards a lepton number of 0. And then for charge, before we've got minus a third, and then after we've got -1 plus 2/3. So we've got charge conservation happening as well when the down quark throws out the W- boson, which turns, so it's basically turning into these two particles. Okay, and then the W- boson decays. They're very short-lived, these W bosons. So then it decays into an electron and an antineutrino. And again, that interaction there, the thing that happens right there, obeys all the conservation rules. We've got no leptons before, and then afterwards we've got 1 and -1, so total of none again. We've got charge conservation because we've got -1 there, -1 there, and that's 0. And baryon conservation because no baryons, no baryons. So in each of these, actually, once you've done a bit of practice at it, they're dead easy because it's just like basic arithmetic, just working out what's happening at each interaction. Okay, so positron decay now. You might want to pause the video here and actually have a go at these yourself if you like. But positron decay, you've got your up quark decaying into those things. So again, you've got an up. So I suppose I should say here that quarks, yes, well, that's covered by baryon conservation. Quarks are always turning into other quarks. Leptons are always turning into other leptons. Okay, so there's your up. And it's going to decay into a W plus and a D this time. Charge conservation is the one that settles it, whether it's plus or minus, because this one is plus 2/3, that one is +1, and that one is -1/3. So plus 2/3 before and plus 2/3 total after that moment there. Then the W plus decays into a positron and a neutrino this time. And it has to be that because charge conservation, +1 before, +1, +0 after. Lepton number, none before, +1 and -1 after. Baryon number, no baryons, no baryons. Okay, and lastly, electron capture. Now this one's slightly different because this time we've got two particles interacting, and that turns them into these other two particles. So this time we draw our up. Now it doesn't matter which of these you draw first, but it will change which W boson you've got in the middle. So I've got my up interacting first. So the up is going to turn into a down and a W plus. And then the W plus hits the electron coming in there, and they interact and they turn into an electron neutrino. And so charge conservation again, 2/3 goes to +1 -1/3. Lepton number, none, baryon number, a third, none. And then on the other one, same thing. Okay, so then, while they may look horrendous the first time you look at them, I do think these are things you can get very comfortable with a bit of practice. And here is an exam question. Okay, so this is beta plus decay again. And so we know, to cut a long story short, that if that's the anti-lepton, then this needs to be the lepton. And then charge conservation, we've got +1 coming in, none coming out, so this needs to be charge of +1. So +1 coming in and a total of +1 coming out. So that means we are W plus and a neutrino, that one.